So let's review this worksheet, which is a review for our test. Let's be crazy and start in order. So we're looking at number 1 here, and just so you understand, I'm adding the idea of sublimation and deposition, that phase change from a solid directly to a gas, and also the idea that deposition from a gas directly back to a solid. We're adding that into our thermal equations here, but that shouldn't change our understanding of anything. Any case, looking at number 1, okay, if the heat of fusion of iron is 0.209 kilojoules per gram, and of course heat of fusion is the amount of energy it takes to melt, okay, a gram of iron. If you look at that value there, which of the following choices would be an appropriate value, okay, for the heat of vaporization of iron? Now, if you look at the answer, I've got 6.3 kilojoules here. Now, going through the choices, I want you to understand something, that if we look at the heat of fusion, which is 0.209 kilojoules per gram, understand that that value, okay, is hard to compare when your other choices are in different units, right? We have kilojoules here, okay? We have kilojoules written here, and we have joules here. So what I did is just essentially converted them into all joules per gram, okay? And we should recognize to do my 0.2 kilojoules or 0.209, I converted the joules, and essentially what I did is I times by 1,000. Any case, if we look to the right of this, I drew a little diagram here, and we should all be aware that heat of vaporization is always going to be larger than the heat of fusion, which means on the curve, this line should be longer in a heating and cooling curve. Why? Well, if you take the time, like we've done in other problems, and we've measured the time it takes to actually vaporize something, it's going to be longer, assuming the energy that we're absorbing is, of course, what? Constant. There's going to be less time here for the same energy, okay? And that's why heat of fusion is always smaller. So what I'm looking here is for a larger value, okay? And that larger value, okay, could be 2260 joules per gram. That is certainly, okay, bigger than 209, okay, in choice A. But I know that's the heat of vaporization of water. So you're not going to use that, right? So because this is already a value for water, different substances will have unique heats of vaporization. So that can't be right. And you say, okay, so 209 joules per gram, 208 is less, that's not going to be used, that makes sense. I can jump down to 210, hey, that's bigger, so that could be a value that I choose, but it's not bigger by much as I speak to it below here. It's still too small. We're going to have a much larger increase, and one way to remember that is the heat of fusion of water, and if we just look up here, the heat of fusion of water is 334 joules per gram. The heat of vaporization for H2O is 2260. Much, much larger change, and why? It takes a heck of a lot more energy to change a liquid to a gas than it does a solid to a liquid, okay? A lot more energy changes there. So the one that is larger, that is not another compound that's listed, because you shouldn't be able to have these memorized, is 6.3. Okay, so let's go on to now number 2. All right, so how many joules of heat are released when 12.71 grams of ice at 0 cools to negative 30? I want you to do what? Can you understand? Draw! Please draw. Why? Because you can visually see what's happening here. All right, so party people, when I draw this, here's what I did. It's a cooling curve. Energy is released, okay, so therefore my curve goes down. But if you look at the problem, it says that ice at 0, and now we're at 0 right here, we're at 0 right here, is going to go down to negative 20.3 degrees Celsius, okay? And so what we know is if we have ice and it's just getting colder, we didn't say we had water that froze. All we did is we had ice at 0 and it went down. Ice can be at 0, okay? So we're starting in this point right here, okay? And of course, what's going to happen is we're going to essentially go down till negative 23. So this is not a phase change. I have ice at 0 and it cools to negative 20.3. So we're still in the what? The solid phase. So this is the solid phase. We should all be aware that this is the solid phase here, okay? And of course, that's what we have. And so because it's a solid and because we're not at a phase change, we have a what? Change in temperature, all right? So the change in temperature means we have MC change in T, straightforward. Now, what's really important, though, is that you understand that we're dealing with what? Ice. So in these thermal equations where we have a change in temperature, we're going to make sure that we're dealing with the mass of the ice, the temperature change of the ice, and more importantly, the specific heat of the ice. That is something that's going to be given to you. This is not the specific heat of water. If I look at my cooling curve, water, okay, does not exist, or liquid water does not exist at negative 20.3. So we had to make sure we understand there was no phase change. It was just ice going down. And if you're having confusions about this, remember this comes up again, this comes down, this would be liquid water, this would be the phase change, right? Okay, and this would be the other phase change where a liquid or a gas goes. So again, just understand that we're just a solid, okay, that's getting colder. That's all. But we need to make sure we have the what? Specific heat of the solid. All right? Any case, I plug these values in, okay? I plug these values in, and what do I get? I get this raw number. I've got to round to 3 sig figs. And I look at my original measured values, I've got 12.71, and I measured these temperatures. Everything has 3 sig figs, so party people, I reduce or round this to 3 sig figs. Looking at the 5 here and seeing that it's 5 or greater, so that makes this next one go up to 532 joules. I didn't ask to convert this to kilojoules, I do not think, and so we're good. All right, so that, again, you have to be able to identify where are we at this curve. And if I look at the bottom, this one right here, okay, we were just cooling, and we're going this way, of course, but we're just here. We weren't at a phase change, so it's important that you can recognize that. Okay, so number 3, and this is new today. Is sublimation endothermic or exothermic? Well, sublimation is essentially a solid becoming a gas. So there would be my heating curve, and there would be my solid, there would be my liquid, and gas, and a solid going to gas. Okay, so it's important that we can recognize that. All right, so it's endothermic because my curve has to go up. So I just said sublimation is endothermic because energy is needed to be absorbed to change a solid into a gas. Gases have tremendous potential and kinetic energy. How do you get to that point? You have to give them energy. So it's as simple as that. Sublimation is endothermic. Now we should know that deposition is the opposite, where we take a gas, change it to a liquid, directly to a solid, so that's a gas to a solid here, and we're going down. So that would be exothermic, okay? So important we recognize that. All right, number 4, another thermal equation problem. And I suggest you what? Draw to see what's going on. So here we go, party people. And people that want to go to the party just don't know where it is. So let's go. Number 4. Calculate the amount of kilojoules of energy, all right, let's put this up here so we know, is needed to completely sublime 193 grams of CO2 at its what? Sublimation temperature. So this question is screaming to you, phase change. And how do I know? Because we want to completely sublime something at its phase change temperature. Okay? It's just like if we want to melt ice at 0 degrees Celsius or boil water at 100, we're at a complete phase change. And here's my nice little drawing, okay, where I have a solid and going to gas, and of course my phase change is right here with what the kinetic energy. This will be temperature, this would be time, right? And so I'm just looking at a phase change. Now, because there's no change in temperature, I just have this formula. Q is equal to mass times the heat of sublimation, which is given to you in the table above, or the information above. So that's all I'm doing here. I'm going to take that, and I can't use, guess what? I can't use a formula that gives me change in temperature. You better know right now that at a phase change, whether it's sublimation going this way or deposition going back, it's still a phase change. Temperature stays constant, so we can't use our change in temperature thermal equation. So we use something like mass times heat of vaporization, mass times heat of fusion. In this case, we call it heat of sublimation. And this is a value given to you. So mass times this. And so when I plug it in, party people, I get that many joules. Now remember, they wanted kilojoules. All right, so I can do this. All right, and so I convert to kilojoules once I plug that in. And I round to 3 sig figs because all of my measurements, are 3 sig figs. Okay, so important you can see that there. All right, so straightforward, the answer is 114 kilojoules. Just a straight plug-in, but it's really the identification. We just had a phase change. Can't use a change in temperature. We had to use one of those mass times constant formulas. And this is our new one because it's subliming. Number 5, we're going to calculate the amount of kilojoules of energy that's needed to completely sublime 193 grams of CO2 initially at negative 50 degrees Celsius. Now, because I have a negative 50 degrees Celsius, and I know from the previous question that the temperature that the solid CO2 starts to phase change into a gas, sublime, is actually 180 Kelvin. How do I relate Celsius to Kelvin? So what I did initially was I converted my Celsius to Kelvin. And from the reference table, I know that Kelvin plus Celsius, or Kelvin equals Celsius plus 273, table T. And I took my negative 50, and I added 273, and I have the actual temperature that the CO2 started at in this problem. And guess what I did? Okay, I made a drawing. Yes, I can speak. And in this drawing, I saw that if I'm starting at 123 degrees Kelvin, I'm way below its sublimation point. Okay, now in the problem, okay, I need to calculate the amount of kilojoules, make sure you recognize that, that's needed to completely sublime 193 grams of CO2, initially at negative 150. So if you think with me off to the left here, if I'm below the sublimation temperature, I haven't sublimed yet, and this must be the solid phase. We're trying to become a gas, and this is a solid going to the gas. So before I can completely sublime it, which would be right here, I've got to heat it up to the sublimation mark. And as you can see, okay, get rid of that drawing, we're going to use MC change in T because guess what? There is a change in temperature. All right, so that's important. So we've got 2 steps here. Okay, we're going to heat the solid to its sublimation mark, and let's get to that. All right, and that's what we have right here. So I'm going to heat the solid to its sublimation mark. That's the first step, or to its sublimation point. And because I'm heating the solid up, it's MC change in T. Just be careful with this. We're going to use the mass of the dry ice. We're going to use the specific heat of the dry ice and the temperature change. Now that I'm both in kelvins, okay, I could subtract them and get 57. And when I do that, all right, I get 9,350.85 joules of energy. Okay? And, hey, I convert to kilojoules, divide by 1,000. And notice something. I added to 114. Where did I get that? Well, that's only the first half of the problem. Remember, the problem wants you to take the solid below its sublimation point and completely sublime it. So, party people, we're going to have to do what? Sublime it at this phase change here. All right, but guess what? The problem in number 4 used the same value of 193 what? 193 grams. And it times it by the what? Heat of sublimation. That's what this formula is here. Can't use change in temperature. So this value here, okay, is exactly what we do here. No need to recreate the wheel. Okay, so I'm just going to use the value that I did in what? Question 4, which is written above here. Okay. And I'm just going to include it here. I'm going to add these two together. And when I do that, I get 123.41385 kilojoules. And of course, I'm going to round to 3 sig figs because all my measurements, okay, are the least number of sig figs is 3 in all my measurements. I have 193 sig figs. 150 degrees Celsius is 3 sig figs. That decimal place after the 0 makes the 0 count. Okay, cool beans. Let's go on to 6. In your worksheet that we did yesterday, we had a multiple step problem, and so is this one. So let's read it first. Number 6, calculate the kilojoules of energy needed to completely vaporize at 100 degrees Celsius 29.3 grams of ice if it's initially at a negative 0.8 degrees Celsius. Not written very well, so I kind of ad-libbed it. So we're going to take ice that's initially at negative 15.8, well below its freezing point, and then we're going to completely vaporize it at 100. So in order for that to occur, I'm going to ask you to draw again. And if you look here, party people, when we draw, we can see that this is going to be 1, 2, 3, 4 steps. I'm going to heat up the ice to 0. I'm going to melt the ice. I'm going to heat the water. And then I'm going to completely vaporize. You can see if you draw the 4 steps. And I use the what? 29.8 grams is going to be the same for ice as it is water, okay, as during the phase change. And of course, what I do is I add them all because we're all going in the same direction, which is up, which means we're adding energy to make all of these happen. I multiply them together. Notice the temperature change, okay, for heating the water is 100 degrees. I have to take it from 0 to 100. And notice the temperature change in the first heating up the ice is 15 to get it to 0. So you can definitely take a look at the key a little closely, but those are the 4 steps. Okay, notice where the change in temperature is, only for the solid heating and for the liquid heating. The 2 phase changes have to use the what? The thermal equation that doesn't have the change in temperature, but have the correct what? Heat of vaporization value and the correct heat of formation. Add these all together, okay, convert to kilojoules, round to 3 sig figs, and you got 90.7, okay? So that's really important you see that. All right, continuing on. In number 7 here, we want the final temperature of water if 2,200 joules of energy is released. You got to read the question, released. Okay, if the energy is released, okay, that means that the final temperature of the water has to be lower if the water loses heat. It gets cooler. All right, so this is a classic question. And because we're talking about water in the liquid phase, guess what? We have a change in temperature. So we use a thermal equation of Q equals MC change in T. I plug in my values, make sure I have the right specific heat for water, okay, which is 4.18. And I'm going to, what am I going to do here? I'm going to solve for change in T. So algebraically, these values go underneath. That's what I showed here using my algebra, okay. And then I solve for my change in temperature. I know some students want to solve for TF minus I. I think it's easier to solve for your change in temperature, but this is not your answer as some people solve for, okay? Now that's the temperature change. That's how much it goes up or goes down. But in the problem, I'm saying the energy is released. So therefore, party people, the final temperature is lower, and I would subtract that from the initial. Just be careful of this question, because I could have given you the what? I could have given you the final temperature and said, hey, give me the initial with the same amount of energy. But of course, I would have said, you know, set this up a little bit differently. But if I gave you the same numbers and said energy was released and I gave you the final temperature, you would have subtracted because the final temperature, you would have added, okay, because the final temperature is lower than the initial, you would have added this to get the initial temperature. Just be careful of the wording. And of course, I could have changed the wording up here and said what? It was absorbed. So there's 4 different ways I can write this question. We've seen it. I think this is the easiest way. Okay, but a classic question nonetheless that you will see. Okay, mark my words. If you can mark words. I'm not sure if you can mark words unless you have a transcript. But in any case, number 8. Hey, which of the following represents deposition? Hey, it's the opposite of sublimation. The greatest example of deposition in our environment is water vapor, water gas becoming water solid or snow. And if you know, snow can be compacted, is kind of airy. Why? Because it's gases are really far apart from each other. So when they go directly into a solid phase, they're going to have gaps of air. Okay, we know that snow isn't solid ice because it doesn't fall and hit on our heads like it would in a hailstorm. In any case, we're looking to go to what? A gas directly into a solid, and we must realize that it's exothermic. Why? Hey, gases have higher energy than what? Than solids. So of course the energy diagram, or in this case the heating curve, is going to go down. And it goes down because energy is released. It's exothermic. All right? So that's how that works. All right? Any case, going on to the lab question, this is very much like what we've been doing, okay, in our experiments, whether it's the Cheeto lab or the heat of fusion, the ice cube lab. So notice we're going to have an experiment just like we're going to do in class, or have done, and we're going to do the heat of sublimation of CO2. And because I can't directly measure the CO2, and by the way, all of these labs are the same. I'm going to take the energy from some substance that I can't directly measure, but I'm going to make the assumption that all the energy gained or lost by the water is the same energy gained or lost by the substance. This could have been the Cheeto here. This could have been the ice cube. Now, in this case, we know the solid trying to go to a gas, which is sublimation, is endothermic. So when we have a cup here, and I have some water, we're going to drop some dry ice. It's going to take energy from the what? Water to become a gas, because gases have higher energy, so the temperature is going to drop. I can't directly measure the CO2 because it's going to become a gas, so it's going to disappear on us, so we can't do it. But the same energy that the solid absorbs is going to be the same energy that the water releases. We've been seeing this before. So I'm going to use the mass of the water, the specific heat of the liquid water, change in temperature. That's all given here. The grams of the water. I have my final and initial temperature. Notice it's going down. It's endothermic because the CO2 is going to grab it. And of course, I'm going to go take my grams of water, specific heat of the water, change in temperature. I do not put the mass of the ice or the Cheeto here, right? You never mix and match thermal equations. This is the Q of the water, mass of the water, specific heat of the water, change in temperature of the water. And so when I multiply that through, I get this value here. And what I'm going to do, energy is never good by itself. I want energy per how much? Per how much what? CO2. When we did the Cheeto lab, this was the grams of Cheeto, and it was the ice cube lab. So I do joules per gram, and I'm telling you I want the unit in joules per gram there. So I divide by the grams of the CO2. And of course I round to 3 sig figs, which by the way, this should have a point here to have 3 sig figs. I can see a little mistake. That's a 600 point there. All right. And then of course the last thing we're going to do is a percent error and talk about the errors. So let's roll on. Okay. Oh, not that way. Let's roll on here. So we got percent error, and it's measured minus known, divide by known times 100. And all I did was take the measured value, which is 600 point, minus 591, which is, by the way, where did I get that? That's the known that's given to you that we've used for other problems in the top of the page. Divide by the known times 100, and you get 1.5% error. If you were to get this wrong, no double jeopardy based on the error there if you did your math right. And the last question, I guess, okay, what were some of the errors? In calorimetry. Calorimetry is where we're going to use water to measure energy changes in it. Okay, we're assuming the system is closed, but it's impossible. Okay, it's an ideal scenario that can never ever be. Heat's going to find its way in or out. So in this problem, some of the heat was lost to the surroundings, and heat is lost always in calorimetry experiments. Always remember that. So the energy change wasn't exact. Now, if you think about this problem, we had hot water going down. Yes, I'm still at school. We had hot water going down to a warmer temperature, but not colder. This warmer temperature water is way above room temperature, which is normally 22 or so degrees Celsius. So the heat would have escaped out to the environment and it would have made a bigger temperature change. That's why we're a little bit above the known there. Okay, in any case, the heat is lost. Hope that helped. and take a look at the key in detail if you want to work these out, but definitely take a fresh piece of paper and do these problems again. I have a blank at the website. All right, so hope that helped, and good night.